Welcome everyone. This is a Torque Theory virtual classroom series. We're kind of doing a hybrid classroom today. I'm kind of excited about this. We have a couple of guests here at our Louisville location and a couple of guests, I understand, up at our New Berlin, Wisconsin location. So the rest of us are streaming from the World Wide Web, staying safe. We're actually, Ben and myself are located at the Louisville office as well, but just in the spirit of safety and in the times that we've gone to sort of private rooms to be able to take our mask off and speak clearly and present. So my name is Kyle Hurst. I have been with Rhino Tool House through some of our acquisitions for about 15 years. That is crazy for me to say. I got into this business in 2006 from General Electric, where I was a manufacturing engineer and a supplier quality engineer prior to this. On the line with us, who will be presenting with me today, is Ben Mayhew. Ben, you want to introduce yourself?
Yeah, sure. Thanks, Kyle. My name's Ben Mayhew. I'm an applications engineer with Rhino Tool House. I've been with the company for almost 5 years now. I work out of the Louisville office, primarily covering the Ohio Valley region, but I also assist with other regions as needed. Yeah, it's been a good ride. I've learned a lot, and hopefully we can impart some of that knowledge to you guys today.
So we're about to begin. I will continue with the presentation. We will have a chat. So if you have questions, we ask that you chat those in. Stephen will act as our moderator. He will attempt to let Ben or I know. You do not have to wait to the end to send questions in. If they pertain to a certain slide or a certain topic, go ahead and get those in. He'll work with us to kind of get them to us as best he can. If more than one come in, he'll just work through those in order or just to work through them all. So just bear with us. And here we go. So as I mentioned, I've been in this business now for about 15 years. I came from GE from the manufacturing side. And to me, it was a long time ago. So tools were much simpler then too. But torque was just one of many things that as a manufacturing engineer I was responsible for. And I don't know that we understood it or that I understood it in particular, other than is that screw or is that bolt tight? I can't even, I guess I'm getting old, but I can't even particularly remember torque values around the fastening processes on my line. I know they've come a long way since then, and I'm sure that the engineers of today at that plant could tell you step by step and station by station what those are. But I really took it for granted. And when I got into this business, I don't think I understood the intricacies and the nuances of torque and why small changes can mean big differences in both your process quality and your manufacturing. And so today, we're going to go over many of those things for you. Hope to answer some questions. And I think everybody's going to walk away with a little bit better understanding. So at Rhino Tool House, our mission is to identify and deliver the world's most innovative industrial solutions, right? So that really stands out to me as part of our mission. And that's what we're talking about today. So the big change from when I was a manufacturing engineer into today's world is those tools were much simpler. They were probably clutch air tools. They held a tightening tolerance of probably around 10%. And today those tools are fine for certain applications. There's probably battery clutch tools that are doing those jobs today in a lot of places, but a lot of us have safety and quality critical joints that are using much more sophisticated tooling than at the time, and the nuances of torque are going to be much more intricate when we talk about those. So I think you'll come out with a better understanding of why those tools are so important and the level of information that they provide for you and the value of that. So the last part of this is that I want to touch on here is that we work to empower our customers, right? So, and what I mean by that is this training today is one of, we hope to be many, and we hope that our customers learn from this and benefit from this. And we want them to be knowledgeable, not just on their processes, but on the particulars and on the tools and products that we sell, because we know that if you know them and understand them, that we think you'll love them and you'll probably buy more of them, hopefully from us. So at RTH, we have many locations and regions now. We've grown quite a bit over the past 2 years. We cover around 36 states or more. Most of our sales engineers live in those locations. We have several key offices and repair centers around the country. The two largest office locations are New Berlin, Wisconsin, and Concord, North Carolina. We have repair centers in New Berlin, Louisville, Kentucky, and in Hanover, Pennsylvania. And then we have sales offices in Minnesota, Iowa, Michigan, Ohio, Kentucky, and we have a manufacturing location in Indiana. So a lot of people have been asking us lately, what does the Rhino Tool House logo mean? So what it's meant to mean is it's meant to be a combination of the name Rhino and Tool House, the two major brands that came together to form this entity. And the rhino, of course, is symbol of a rhinoceros. It's a strong animal. It charges forward confidently, right? It doesn't look back. And the house is meant to symbolize the foundation and the support that we want to be for our customers. We want to be there for them when everything is going well, and we also want to be there when you have a problem on the floor. We're going to be there next to you to support you when you need that help. So I'll just touch on a couple of these and we'll get into the presentation. So a few of the things that I think stand out that pertain to this this webinar right now are national footprint. We likely have customers coming to you from all over the country. Service minded. So our goal is always to make our customers more knowledgeable, to help them make their products better, and to make sure that we're there for them when they need us. And the Tool University customer education, I hope that shows through when you get through with this today. It shows our commitment to our customers and how much we want to be involved and invested in both their plants and their processes. We have a couple of different levels of support. We have sales engineers in the field. They work with regional managers, but we also have application engineers and material handling specialists. We have product managers. We have sales support people, which we just talked about. Project management. So one of the things we realized early on is that we can't leave it up to our customers or our vendors to manage projects. Many of those projects are crossing vendors. And so we actually took that responsibility ourselves. And then service centers. So we have 3 service centers right now in the United States. All of those service centers are ISO 17025 accredited, and we can calibrate tools up to about 4,000 Newton meters. So now to the class itself. So what are we talking about, right? When you boil it all down to a single point, you're talking about each fastening, each joint. And there's a lot going on there in terms of physics or forces inside of that joint. There's the 2 usually pieces of material that we're joining together, which are represented in purple. There are shear forces, those trying to pull away from each other on that fastener. We're using the fastener itself to provide clamp load to hold those 2 pieces together. And the fastener itself is providing tension. So it's actually pushing back like a spring. So why do we do this, right? I think everyone knows part of it's just quality, but consumer safety, more and more, there are single point failures that can cause accidents, they can cause injuries, they can cause even death. Production costs, so how do we make our processes more efficient? How do we build it right the first time? And then the quality and the warranty expense. Everything today has to be better, it has to be faster, and it has to be right the first time. There's no margin for error in today's world. So what are we really after, right? We talk about torque. This is a torque theory class. But when you talk to design engineers, when you talk to the people designing the parts and the equipment, what they're really after is clamp load, okay? But clamp load is not as easily measured as one would hope. So there's several ways to do that. One would be to actually measure the length of the fastener. When we tighten a fastener and we actually begin to stretch it or elongate it, you can measure the clamp load applied through the elongation of the fastener. The next way to do it would be to put a load cell in the joint. So underneath the head of the bolt, we would put a load cell washer there, and we would actually sense that clamp load as we tighten the bolt. The third way is that you could actually have a bolt with a strain gauge transducer or a strain gauge in the bolt itself. This is pretty common in power plants and nuclear power plants, things where the fastener itself is so critical to safety and quality that they don't mind the extremely high price of a fastener with that in it. But the simplest, the most straightforward way to do this is an indirect measure of clamp load that we all know is torque. So what is torque? So torque is force times distance, right? It is a static, in its simplest form, it is a static force about a point, right? So we show that here in the demonstration with a wrench. It could be a person on a bridge. It could be anything. Essentially, torque is applied. It is a force about a distance, about a single point. In this, we're going to do a little bit of definition. So dynamic torque, you'll hear that term several times. You'll hear that when you talk to our sales engineers in the field. Dynamic torque is the torque that we're measuring as we are turning the fastener. So we have overcome some level of friction and the fastener is in motion at this point. The opposite of dynamic torque is static torque. So static torque is taking a fastener from rest and moving it into motion. So at this point, we have to overcome friction to begin to move the fastener. Prevailing torque. So prevailing torque is the amount of torque that we feel as we fasten, but it is not applied to the joint itself. So what I mean by that is if you think about thread cutting or moving through some sort of Loctite or nylock nut, trilobial fasteners, right? It's requiring some basic amount of force for us just to spin the fastener to begin to close that gap to actually get the nut and bolt or just the bolt snug on the part itself. Residual torque is very similar to static torque. It is usually measured after the peak. So I begin to move the fastener or the nut, and it is the amount of torque just after that. And then breakaway torque is very similar to that as well. So breakaway torque is the torque required to loosen and tighten fastener. So you'll hear those several times. There is a lot of overlap between static, residual, and breakaway. There are fine nuances to the difference. But for today's lesson, the most important things here are dynamic, static, and prevailing. So when we talk about torque, you'll oftentimes see it as a graph. Torque is typically the y-axis, time or angle will be the x-axis, and it will begin to go about some distance. So in this case, we're going to look at time, so torque over time. A typical torque chart looks a lot like what you see on your screen here today. We tighten a bolt or a nut to some basic point, and then we stop that fastening prior to the fastener failure. The peak dynamic torque is what you see at the top of the curve, right? And what we're trying to showcase here in this graph is the relaxation of the joint or the settling. So what that means is that we ran the fastener to some point along the torque curve. But over time, if this chart continued out, that fastener would relax for some period of time. It will relax differently at different periods in time. So just after, if I take the reading with a wrench just after fastening versus if I took that reading with the same wrench, say a day later. And there will be some period of relaxation to where that tops out. So the difference between a day and a week, there might be zero, but the difference between one moment after fastening and one day after fastening, you will likely see a significant difference. And that's basically the case because you will see it could be vibration. It's going to be the parts in between that shear force and the clamp load settling, but there will be some relaxation in the joint itself. So a little more definition before we get going. So we talk about hard joints and soft joints. What do we mean by that? So ISO has defined those two things. And then you'll hear about a third type that they don't define, which is a medium joint. So a hard joint is exactly what it sounds like. It is something that goes from 10% to 100% of torque in under 30 degrees. So this is something that as you tighten it, as the bolt becomes snug, the distance in rotation is very small from the time the bolt head touches the top part until you reach your final torque. A soft joint is the opposite of that. So Greater than 324 degrees of rotation. This is the type of joint that as you feel it tighten, you can sort of feel it compress. You can almost watch it compress as the two parts are held together. And then a medium joint would be something in the middle. Most joints will be hard or medium. A true low torque soft joint is rarer than it sounds, although you will find them. They oftentimes have gaskets. They can present a high degree of difficulty when you're fastening because they tend to be the most inconsistent when you fasten them. So what types of joints will you find in the field, right? And what we mean by this are what level of sophistication or confirmation or information is needed on the manufacturer side to understand the quality of that joint. So the first and lowest class is what we call a Class C. So a Class C joint might be like a speaker cover or a plastic piece that's just a covering piece that it doesn't really affect the quality or operation of, say, a vehicle. It's could result in a warranty claim, maybe not. It's probably a squeak or a rattle type thing. In today's world, we're trying to have less and less errors to start with. So this is the type of thing that we're probably measuring okays, not okays. We're probably counting screws. We want to catch signaling. So we want to know they were supposed to put 4 screws on the speaker wire. Did they, or on the speaker cover, did they fasten 4 screws? Were all 4 of those okay? But we don't necessarily need a number or an angle of rotation about those. So the next one is quality critical. So if you think about this with an automobile, this is the type of failure that might result in a breakdown, right? So, and what I mean by a breakdown is a safe breakdown, right? So let's say the car won't start, okay? So with this type of information, we know it's going to result in a quality or a warranty claim. We know there's going to be some cost of repair. And for this type of joint, we need more information. So we're going to need a transducerized tool or a current control tool that gives us a number. It will likely give us an angle of rotation, so we have some certainty that they use the right screw or the right bolt. They have the right number of washers or grommets in the fastener, or some sort of click wrench, right? Where we know that they can get this down to a specific point. Click wrenches are very controlled. Can we get that tight enough? We are almost certainly counting the number of clicks and making sure that they do the correct number of fasteners. And the final and most critical is safety critical. You'll hear these called delta joints, A joints. This would be wheels, airbags, seats, seat belts. These are the type of things that when they fail, someone can be hurt, someone can even die. And for these, we need the highest level of sophistication and information. So we're not only going to use a transducerized tool to measure torque and angle, we are also going to likely pair that with some other intelligence. So it could be a positioning system so that we know that not only are they using a tool that runs to a specified torque without any input from the operator, but we know that they're using it at the right position. We know that they do all 4 bolts on that seat as opposed to just 1 bolt 4 times. We would also use, in this case, maybe a multi-spindle. So we force that level of sophistication without having to rely on an operator to move it from A to B to C to D. One note you'll see on here is there are different types of transducers. So a torque transducer is a simple gauge, a strain gauge, that actually feels the torque applied to the fastener through the tool, and it is what's giving us that numerical measurement. So a Class B torque transducer and a Class A torque transducer, the difference there is really the level of sophistication, accuracy, and certification in the transducer itself. Most tools you will find today on the market are Class A. Your sales engineers can help specify which ones are and which ones aren't. Class B are meant to help you at a lower cost point with a lower level of required sophistication, like what we were talking about, the difference between safety critical and quality critical. So this is a pretty complicated chart, but what I really want to show here is a few things. And I think most people who have worked in a plant and have done fastening or have seen torque curves understand this if you've seen enough of them at some point, because you've likely seen a bolt failure. this is a typical curve to where you reach a bolt failure. So the most sophisticated and the highest level of clamp load we can provide with a single fastener is when we reach the yield point. So you'll see the yield point, or where you can notice the yield point on a torque curve, is at the top where the slope of the curve changes. So you'll notice in this curve, the slope itself is very steep, and then it begins to almost roll over. So what that means, the physics of what's happening at that point, is that is actually the point when the bolt itself is beginning to stretch. So that is the point when we are nearing failure of the bolt, but we are also, prior to that, we are providing the highest level of clamp load possible in that bolt. There is fastening that uses yield point. You'll see it oftentimes in powertrain. Most fastenings are not done to yield. Most fastenings are done to what we would call like a proof load, which is a safety load or an engineering load, where they know that bolt can do probably 1.5 times the amount of torque that they're going to apply to it. Right, so they will target 50. The failure point of that bolt is probably at 75 or 80 or even above. One of the things here to keep in mind is oftentimes customers will say, well, how did that bolt get loose? That bolt was tight. What can happen many times, especially in multi-fastening situations where I have a part that requires to fasten around the edge of an object, such as like an oil pan or a gasketing situation, what will happen is that first bolt was tight. You're actually correct. But as the other bolts have tightened, we have changed the flatness of the two parts laying against each other. Remember the two parts and the shear forces. And so we are now below that 50% of proof load. And what happens at that point is that bolt itself is susceptible to loosen, not just a little bit, not a settling effect, to actually come out. So Ben, I'll let you take over from here.
All right, sounds good. Thanks, Kyle. So to continue along this academic sort of cerebral line that we've been going down, now we're going to take what Kyle's talking about and we're going to actually go through the 4 stages of the tightening process. In here, it's called the 4 zones. The first one is rundown or prevailing. And then we go to alignment, threshold, snug, clamp load, start point. They're all kind of the same term, loosely applied to exact same point in the curve. The next phase is the elastic clamp zone. And then finally, we have post yield. So we'll break all those down here real quick. So the first one is zone 1, rundown and prevailing. You see it right here, kind of got a blow up of that graph for you on the right. So there's a lot of things that happen here in this rundown, or at this point in the rundown. This is what occurs just before the fastener makes contact with the surface, right? So you could call it a free run, but really you're drawing down the threads of the fastener. The next thing that happens here, I mean, there is no clamp load. The parts are not tight against each other yet. The other thing that happens in this zone is this is where we'll run into prevailing torque. And without a specific strategy and the right tools to address it, prevailing torque can be very challenging to overcome. So we're going to talk about prevailing torque here a little bit more in a second. But essentially what prevailing torque does is all those things that we were kind of talking about before, right? There can be some added friction. There's greater potential energy that we need to overcome in order to actually physically drive the bolt into the application and to begin to apply that clamp load. And then there's 2 kinds of prevailing torque. There's the on-purpose kind, and then there's the unintentional kind. One is obviously good and one is bad, but both need to be equally accounted for and addressed for a successful fastening. So again, the rundown zone is everything that occurs before clamp load begins. And if you remember our diagram from the beginning, that is the point before the 2 pieces of our application actually draw together. Okay, so let's talk a little bit more about prevailing torque. First, there's intentional prevailing torque, right? That's what Kyle was mentioning up front. Those are the kinds of things that we do on purpose, either for a safety specific reason, with a trilobial fastener or an oblong fastener, commonly found in seating applications. But there's always a specific design purpose for the prevailing situation. And some of these are things like crimp nuts. You have nylock, Loctite, the different kinds of bolts we were talking about. Those are all examples of intentional prevailing torque that need to be accounted for during a rundown in a fastening. Then we have unintentional prevailing torque, which is not a good situation. But fortunately now, with the quality of the tools and the intelligence that's built into a lot of tools anymore, we can account for those things, or at least identify them early enough in the rundown that we can address it while parts are still in station before they leave the station and we send bad parts forward. And here's just a few examples. I'm sure if we talked for a few minutes, we could all come up with a whole bunch more. But really, one of the things that unintentional prevailing torque does, and if you remember back to our college level physics formula up front, what it's doing in terms of the physics of fastening is it's adjusting the coefficient of friction resident in the application. And that obviously is going to change the dynamics of fastening and applying clamp load to that application. So there's a few charts, show you kind of what it looks like. The chart on the bottom right is a great example of something that you might see with a like Loctite on the tip of the bolt, just as an example. Okay, so then the alignment zone, zone 2, the seat point, threshold, these are all common names for that moment in time where the head of the fastener has made contact with one side of the application and we're beginning to apply clamp load to the application in the joint. So, you know, on this graph, it's at the very end of the rundown zone. And what happens here and the strategies needed to address this specific moment in time is going to be extremely dependent on the type of joint that we're dealing with, whether we're talking about a hard joint or a soft joint. And also some of the things that matter here are exactly what kinds of materials we're fastening. For example, plastic is a lot more susceptible to speed than steel is. So those are just things that have to be considered at this point in time. So zone 3 is normally what we were talking about in terms of where you'll find that proof load, the elastic clamping zone. So in zone 3, what we're doing with the fastener is we have turned it into a spring, basically. And that is what that spring action as we stretch the bolt into the joint is what's applying the clamp load to the joint. This is for most, not all, but for most applications, this is where you will find your target torques. So the fastening within this zone is absolutely critical. Being able to measure most of the time what's happening in this zone is critical. And as you can see, this zone accounts for our primary focus when it comes to fastening applications, because this is where we need to know exactly what's happening, what our data points are, and whether we've accurately fastened that joint or not. Now the next zone is zone 4, and that's post yield. Most, like Kyle was saying, most applications, you know, in the 5 or 6 years that I've been working at Rhino Tool House, I've only seen a handful of yield applications. but it's critical to understand what happens here in terms of the physics. So what you'll have in this yield or post-yield zone is, you remember how I said that we were taking the fastener and we've turned it into a spring in the elastic zone. So if you were to back that fastener out in the elastic zone, the bolt would return to the same length that it was before you started fastening. It's elastic, right? It retracts back to its original length. However, when we get to zone 4, what's actually happened is that bolt and its material, we've exceeded the tensile strength of that bolt, and we've stretched it past past that point. And so it's actually turned into what we call plastic, and it will not return to its original length at that point. You've permanently stretched that bolt. Again, like Kyle was saying, there's some times where that is designed for and accounted for and called for. Most of the time, that is not what we have, though. So at this point, you can see in the graph, basically, torque levels off as angle continues to increase. If we continue to apply torque in the fastening direction, eventually what will happen is you will break that bolt. You will snap the head, or somewhere inside the bolt it will snap, and we may end up having to tap out the remnants of a bolt from the application. But that's what happens. That's why. So now, I guess what we're going to talk about is some of these ways that we can get into error proofing and understanding maybe which tools are most appropriate and applicable based on what we're trying to do and what we're trying to accomplish. So if you remember the chart that we went over earlier with your C, B, and A level joints, this is what we're getting into a little bit in terms of error proofing and ensuring the quality and accuracy of that fastening. So we have levels 1 through 6, increasing in precedent, the same way we increase from C to A. And we're going to talk about all of these in some detail in the coming slides. So as you can see here, the things that we're about to discuss is you go from level 1 up to level 6, or level C, a rank C joint, to a delta joint or a safety critical joint. The intelligence and capabilities of the tools or the systems increase as we move up those ranks. So here's a few examples. We're going to start at the bottom and work our way to the top. But some general rules and guidelines for capabilities, right? Your impact or impulse drivers are rated at roughly 25% of target, all the way up through DC electric tools can be less than 5% accuracy in terms of rated against target. They don't leave, our repair and calibrations department direct drive DC tool unless they're within 2% of target. So these tools can be extremely accurate if that's what's needed. But if that's not what's needed, then maybe we need to look at a different tool. So on the low end of the chart, right, low control, cheap, fast, get the job done kind of tools. I mean, you have your basic impact wrenches. Typically what you're thinking about here is something like a Makita or a DeWalt or a Milwaukee, a tool kind of like that. These tools are great at what they're intended for, but you wouldn't necessarily want to use them on a rank A joint, right? That's not what they're designed for. They don't provide any level of feedback. They're not very accurate in terms of ensuring data acquisition and proper fastening. Great for disassembly, great general purpose tools. So they're good at what they do. But again, as we move up the chart a little bit, sort of your next stop would be your hand torque wrenches, things like your click wrenches, click screwdrivers, So what these tools really are doing is tell you that a minimum was achieved, right? They clicked at a point, a set point. We have achieved that minimum target, whatever that target was. But they do have drawbacks, right? Everything has drawbacks. So they're very operator dependent. There is, depending on the tool, a chance for over torquing. I see this a lot. Once it clicks, people are continuing to pull on it, kind of defeats the purpose, right? So there are pros and cons to these tools. And again, they're very good at what they do. These tools are very portable. They're often very inexpensive. And they can be the right tool for the job. Next is going to be things like your like pulse tools. So impact tools and impulse tools also pulse, as the name may suggest. The internal workings of these tools specifically are a little bit different in the way that the motor works. Again, very good at what they do. They're shut off and non-shut off versions, not always as operator dependent. You can reach very high torques with these without the need for torque reaction devices. But again, the way that they achieve that is by oftentimes having like a hydraulic chamber inside the motor assembly. And that hydraulic fluid needs to be changed over time, which can drive up the cost of ownership. They don't really provide any feedback in terms of torque level actually applied to the joint. So again, like everything we've talked about, they're great at what they do, and they have utility. We just got to make sure we're using them in the right, on the right applications. So the next one, moving up the chart a little bit, would be something like an adjustable impact tool. There's a Panasonic pictured there. These tools are, you can, again, with these kinds of tools, reach very high torques, single-handed pistols. They have a relatively low cost of ownership. They're pretty accessible. Panasonic specifically standalone, or you can tie them into some line control, but they are not transducerized. So you're not getting feedback on the actual torque that's applied to the joint. We haven't gotten to that point yet, but Panasonics are again, great for what they do, and adjustable impact tools are great tools. If we're using them in the right application. As we continue to go up, so now we're in the realm of clutch tools. And clutch tools can be accurate within 10 to 15% of their set points. So we've graduated now to almost the next tier. These tools are very, very good tools for what they do. They've come a long ways. They're available anymore in both, battery powered, electrical powered, air powered, generally low weight with a high torque payout, up to 4,000 Newton meters if you need it. And one of the benefits of a lot of clutch tools anymore is that they can signal, right? So you can start to tell whether the tool clutched out or not. And so now we're starting to get into the realm of line control, right? We can start to batch count in a sense, right? At least clutch count. But especially with the battery powered ones, we found that a lot of these are in high demand, and they often grow legs. Again, like everything else, clutch tools at this point still are not going to give you feedback on actual torque applied. But these are good tools. If you think back to our chart, again, these are tools that we do and have recommended in the at least in the C-level category that we had talked about earlier. So One of the next categories of tools is what we would call current controlled. There are a lot of vendors anymore that make current controlled tools, and a lot of these tools are very, very good tools. And so one of the things with current controlled tools is they kind of came out around the advent of DC tools, DC electric tools, and they started to provide increased accuracy. Really what they do when we say current controlled, and if you look at the cons, right, it says you have to teach the tool on the application. And so that can be a little confusing, but the point, I guess, is that current controlled tools don't have a transducer. What they're doing is that they're measuring the power draw through the motor of the tool and using a formula or an algorithm to convert that to torque applied, if that makes sense. Because of the torques that they can reach, they are invariably direct drive tools. You may require reaction devices depending on your plants or your corporate standard for at what point reaction devices are required. But they do provide a much higher level of accuracy over anything that we've talked about up to this point. They also have started to introduce now at current controlled tools, things like multiple torque settings per tool. A lot of these have fancy LEDs that'll tell you when you've hit a good torque. You can tie into line control with field buses and start to get into error proofing. The next tools that we're going to talk about is a step kind of up from that, in that this is the first category of tools that we'll talk about that actually have transducers in them. And these are tools that we would recommend or are suitable for your A-rank joints or your safety critical or your delta joints. And there's several segments of these actually, but these are the first ones we're going to talk about, is the Transducerized pulse tool, or Transducerized discontinuous drive. I've heard them called a few different things over the years. These tools are pretty new in terms of like the evolution of DC tools, relatively new to the market. Within the last 10 years or so is when these really came out. So there are some that have hydraulic chambers. The two brands pictured here do not utilize hydraulic chambers in their motors. But these are the next highest rank in terms of intelligence and capabilities of the tool loop system. The ability of the tool and the controller to execute nearly any condition or requirement that a manufacturer engineer may have is nearly unparalleled. A lot of these tools, because of their pulsing or discontinuous drive nature, have eliminated the necessity for reaction devices, which if you can eliminate a reaction device is now taking you into the realm of accessibility. You can put pistol grip tools in places that you may have never thought to put a pistol grip before. You can reach inside of a car and fasten something with one or two hands that may have before taken a massive torque arm. So in a lot of ways, these transducerized pulse tools are pretty revolutionary and garner a lot of interest from customers all over the country. The next major advantage gained by transducerizing a tool, and current controls can do this to a degree, is the ability to detect and measure angle. And once we can detect and measure angle, now we've gained the ability to do any number of things. Remember all those unintentional prevailing torque scenarios we were talking about? Well, now we can actually detect them early in the rundown, and we can shut off the tool and identify a bad rundown potentially before we've destroyed the part or destroyed the tool, or with a clutch tool, maybe we reach torque and our tool clutched out, so we think we're good, but really it's cross-threaded and it's not fully seated. So instead of now passing that forward, we can detect it and rectify it in station before we pass bad parts forward. Now, these tools do have cons. Everything has drawbacks, right? Pros and cons to everything. So sometimes because of the pulsing function, these tools can be loud. They do have vibrations in them based on the pulsing function. They're not suitable for all fastener types. The vast majority of fasteners, but not all. And I'd be happy to have that conversation at some point with anybody that's interested. Very, very good tools. If you haven't seen a transducerized pulse tool, put your hands on one, or understood how it can potentially revolutionize, your manufacturing process, I'd encourage you to reach out so you can look at one and see what it might be able to do for you. So a couple more categories of tools. The smart wrench. So these are exactly as the name may imply, they're wrenches, but they're transducerized wrenches. So instead of a click wrench, these actually have a transducer in them. And so with that, we can measure angle, we can measure torque applied. These wrenches are designed for production. These wrenches are designed for quality, for auditing. A lot of them have wireless communications capabilities. But you are at the top end of, if you look at the little arrow here, we're reaching the top end of tool capabilities. They're very, very capable tools that can do a lot of things. They're, in a lot of ways, they're like a transducerized DC electric tool in a wrench. Now, again, they're probably not great for a 4-inch bolt. That's a lot of ratcheting. But they can measure the torque applied. They can respond to commands. They can tie into line control. They're very, very capable tools. So then, sticking with the DC tool theme, DC transducerized tools, in this specific segment, referring to direct drive, sort of traditional DC electric transducerized tools. These are, as of today, the most accurate tools you'll find on the market. They can do more things than I've seen any one customer need them to do. Up to, in most of them, 250 different settings, up to 8 or 9 different fastening strategies built in. They can count, they can multi-channel. Some of them have onboard PLCs, some of them have onboard barcode readers. So the idea as we're moving forward, right, and one of the things we've seen with a lot of our vendor partners is that they want to give you, the customer and the manufacturer, the user, as much capability as you could possibly need. And they want to be able to capture as much of the data as you could possibly need, which is not something that we've discussed yet in terms of data capture, but we will. So these tools go anywhere from, I mean, it says 4,000 Newton meters on the slide. They go up a lot higher than that. These are tools that you would use if you needed to do a yield point fastening. You'd use something like this. Extremely durable, but Anybody who's ever tried to hold on to 100 foot-pounds without a reaction device will understand why we say in the cons that you might want a reaction device. So if we think about what we were talking about in terms of, you know, level 6 critical joints or delta joints, one of the things that we discussed was not only ensuring that in terms of quality and safety that an individual fastener is accurately fastened, but that all fasteners are accurately fastened in any given station, and they're fastened in the appropriate sequence. I mean, imagine if you were at the tire place that you go to get your wheels rotated and balanced, and the guy putting or girl putting your tires back on went just right around your wheel in a circular pattern. I mean, hopefully you'd have a problem with that. There's a reason that we were always told to fasten those in a star pattern. And it, you know, Kyle was alluding to it earlier. It's a concept of crosstalk and affects the clamp load. My point is that making sure that these things are fastened in an appropriate sequence is equally as important as ensuring that they're fastened appropriately individually. If you have a multiple fastener scenario. And there's a lot of systems out there anymore that can do this exact thing. It's not just multi-spindles anymore, although that does exist. There are, you know, more positioning systems coming out every day, and they do exactly this. There's all kinds of types, and they work on all kinds of tools, not even just necessarily intelligent tools. Some of these can work on, I saw one on a basic crescent wrench once. They do require additional hardware in various orders of magnitude. But if you need to ensure that multiple fasteners are fastened correctly in sequence, then that is definitely something that we can help you with. So if you look at the arrow again, you know, we're moving our way up to making sure that all of these systems we're graduating to higher and higher levels of sophistication and intelligence. And one of the key points here is garnering data, because at the end, I mean, maybe we've seen it in your facilities, that as we move deeper and deeper into the 21st century, data drives everything, or is beginning to drive everything, depending on how you look at it. So if we're not gathering data, we're already behind. And what kind of data are we talking about? Well, we could be talking about any kind of data, really, but one of the things that the kinds of data that we're talking about is in-station level data. We're talking about how long, you know, certain things took operators to accomplish, and capturing all of that, right? These are some MES systems that provide paperless work instruction. They're data collection softwares. They tie into almost all the tools that we talk about here, and they can control them dynamically based on the program that you've decided to set them for. We can run videos on these. The point is that, I guess, these MES systems, or these station guidance, worker guidance systems, exist to ensure that after, you know, the design engineers have ensured that if it's built correctly, that it will work correctly, and then we've all determined that we're going to build it correctly, and we've spent hours finding the right tools and strategies and setting up the line appropriately to make sure that it is built correctly. Now, the next thing that we can do is overlay one of these systems onto it to ensure that all of that hard work is not lost in the hands of a team member or an operator, and that we can guide them through the process step by step, one at a time. And we're capturing all that data as we go. So the MES systems are powerful, powerful tools. And, the idea being also, I know one of the things that a lot of our customers struggle with is turnover. If we have one of these system like this on the line, then we can really minimize the impact of turnover, because all of the instructions and the requirements for any given station, for any given build, are on hand in front of the operator as they're building, and their tools are being activated only when needed and to the correct setting. We're capturing all the data from the tools. We're capturing all the time that it takes for certain things to happen. So maybe we can identify if people need additional training. Powerful systems here. But the whole point of this is to start to getting to something that hopefully you've seen the importance of, is gathering and analyzing data. Now, as we gather more data, the idea is to turn data into actionable information. So a lot of the tools that we talked about, a lot of the systems that we discussed, are capable of saving immense numbers of rundowns on board. And while that's a benefit and a feature of those specific systems, it's not necessarily the most advisable path forward when we could be amalgamating that data in some sort of database or a system that can analyze these data using machine intelligence and trend analysis to work for you. To put your data to work for you, allow you to look forward out the windshield instead of in the rear view mirror. Because a lot of times what happens is this data, even if we're capturing it, which a lot of people still are not, even if we are capturing it, it sits in a database, untouched, unheard from until somebody needs it, or until there's a recall or a warranty, and then we go back and we dig it up. But there are systems and solutions out there now that can look at your data as it comes in and analyze it and do trend analysis on it as it goes into the database, and give you maintenance calls or identify early potential problems that may be coming in terms of quality or operations, or maybe we can identify that a tool's starting to fail in the middle of a shift. So some of those solutions can be brand specific, but there are a lot of them that are not. And once we've gotten past MES and data analysis, we are off the arrow. And that is it. So
Hey, Ben,
I guess
we had a question about a different worker guidance system that was called ARC. And I got a little clarification on it. It is a worker guidance system. So the answer to that question is we don't necessarily, or I haven't personally worked with ARC. I don't know if Ben has. There are several systems out there, and there are a lot more coming. As Ben talked about this, the curve of the 21st century of, how do we make information usable? There's going to be a lot of these systems coming out. And a lot of our customers have homegrown ones too. Although we haven't worked with that one, many of our systems will. So we can either do that through Open Protocol, which is a data protocol communication system, or through even like an Ethernet IP or something more traditional like that. So if your company or you're working with a current vendor already on a worker guidance system, we can still assist with implementing many of the tools that would work with that system. So the different tools, the different encoder systems or positioning systems, even some lower level worker systems, worker guidance systems, such as like Pictolights, projected Pictolights, wireless positioning control. We would sort of work as a sub guidance system to that sort of mainline guidance system, if that makes sense. Sorry to interrupt you, Ben.
No, you're good. I mean, I think we've covered a lot at this point. We hopefully now everybody on the line has a little bit better understanding of the physics involved in threaded fastening. Take you all back a little ways to high school or college physics. Things you may not have considered before. And then specifically, hopefully, you know, Kyle and I have helped identify some tools that that are available out there on the market right now, that may be appropriate, more appropriate, depending on what you're trying to do, and educated you a little bit on when specific tools or capabilities within tools may be more appropriate than others.
Ben, can you return to the big slide of the arrow?
Yeah, sure. Let me whoop.
Yeah, perfect. So we really appreciate everybody's time and attention. I know this is a lot to take in. I know we moved very fast. You know, we were trying to, torque theory is great. There's a lot of detail to it. You know, there is a lot of intricacy to it, but the most important part of it is how is it usable for our customers and for our sales engineers, even our own employees. You know, what does it mean, right? I mean, it's great to know something, but if it doesn't help you or make your processes better, what is really the use of it? And so that is where, you know, we want to make sure that everybody on the line knows that Ben and myself, as well as our counterparts across the country, are here for this reason. We want to partner with our customers. We want to be a consultant to our customers in terms of, we know that you have 100 things that are as complicated as torque to worry about, and we can be your expert that you can lean on to help with the detailed and the nuance of these processes. So if you have any questions, please reach out to your Rhino Tool House sales engineers. If you don't know who those people are, you can chat in here or email us, contact us through our website, and we will get you hooked up with our local person in that area, and we will make sure that they help you with your specific process.
Hey Kyle, we had a question come into the chat about, is there a tool that can determine the clamp load? I guess the short answer is yes. That technology does exist. It's not really so much the tool, I guess, in the sense that we were talking about tools, right? It's load cells, things of that nature, like Kyle was talking about. There are specific bolts, very specialized bolts that you could buy that would determine the actual clamp load. So I think you were talking about like a load cell washer, Kyle.
Yep. Yeah. I mean, I think, and you're touching on it. I mean, it's funny. I was smiling because I was going to answer that question. No, but I was going to answer it in the same way with the same words. So, I mean, there's not necessarily, when you think of a tool like we were showing tools, not really. And the reason is exactly what Ben answered, though. So you have to use some other type of device, like Ben said, a load cell, a specialized bolt. And when we sell a load cell, it looks like a washer. The bolt passes through the center of it like a donut hole. It has a wire that connects to an analyzer. Typically, there might even be cordless ones now, I'm not sure. But the problem with it is you're measuring the clamp load, but the load cell's in there. So
Yeah.
it's not necessarily practical for a production environment. Where you would see that in use would be more in like a laboratory setting or a design setting where they want to know how much torque. I need X amount of clamp load. I don't know how to figure this out without actually putting a load cell in here and applying torque and seeing what I get, right? Because then they could translate that and say, all right, we need somewhere between 75 or 80 Newton meters to get the associated clamp load that we need. The real specialized bolts are super expensive, which again, do not necessarily lend themselves to a production environment. The only place I've ever really seen those used is in and around like nuclear power plants. You would probably see them, I would assume, in like government installations where anything nuclear is used. So I don't, and they're even trying to get to more of a simpler, like a go, no go because of the price of those themselves. So.
All right, we got, I guess, Emmanuel, for you or for whoever it was that you're representing, does that answer the question? Okay, thanks, E. All right. Ken or Mr. Trudale, I will get to you in just a moment. Mr. Alexander, can you bring up the zones again? Yeah, sure, no problem. Let me get back into it here. It was, I think you wanted the big one, and it these builds.
I think we have everybody's email address.
There we go.
Stephen, would it be possible for us to email people a copy of this?
Absolutely.
Yeah, that's a good point, Kyle. We can after we're done with this, we'll convert it to a PDF and make it available. I think Stephen has the list of everybody in your emails that's on the line, and we can send this out. And then from Mr. Trudale, would you discuss the determination of the snug torque setting for a torque control angle monitor?
So that in programming, right? So in the graph themselves, obviously there's a way to measure it and go back. In programming in programming a tool, there is a lot of individuality is the way I would put that. Individuality, am I saying that right? But in that it's like computer programming, right? So there's no single correct answer. It doesn't have to be perfect. So the actual snug torque of the bolt is specific and measurable, right? But when we use snug torque in a traditional sense, we're again talking about programming the tool itself. And some of the tools in the software will actually call that snug torque or set torque.
Seat torque.
Seat torque, yeah, there's another one. Same thing. They're talking about when the parts and the bolt have come together and they are snugging up, essentially. We would typically, by default, I would tell my guys and I would teach customers, I would say, I usually start somewhere around 20-25% of the final value, right? Because it takes a little bit of trial and error. And the only way to really know, even by looking at the graphs themselves, is by trying. So typically in a rundown process, you're going to have a pretty simple rundown. So we're going to have sort of a fast step where we're going to run at a pretty high speed until we reach that seat or snug torque. And then we're going to slow down as we enter that clamping zone until the final part. So how will I know if I have that set too high? You will know because you'll tend to overshoot. That's the most common way you will know, or you will always be on the high side of your specification. How will you know if you have it set too low? You will likely know because what will happen is you will be beginning to downshift or slow down prematurely, which can be bad for your tools, and you'll know your operators will go crazy because the tool will go slow for so long. But it'll heat up your motors. And the fastening that should take 2 seconds will take 10 seconds kind of thing. And what happens typically in that situation is that you have some sort of prevailing torque that as we're fastening, we're expecting the prevailing torque to be lower than that amount, that snug torque amount. And something, whether it be like a welding slag or an imperfection in the thread, causes that prevailing torque to pop up, if even for a moment. Even if we cut right through it and it drops back down, remember the tools work like computers. So it is saying, when I see this, do this. And so when it sees that torque rise to a certain point, it is saying, oh, I must have got there, and it would slow down even though the torque drops back down. So usually the symptom of that will be a long, slow run well before you're expecting it.
Yeah, not to give you a really long answer to what
Sorry,
seems like
yeah.
a simple question. No, it seems like a simple question, but it's not. It's always a dance, right? Programming tools, in a lot of ways, we'd like for it to be a science, but there is a bit of art to it. Determining the correct snug torque is a little bit of an art. I think what Kyle said, you know, pick something that's roughly 20 to 25% of your target. Aim for that. But also remember that the speed of your rundown is going to play into the actual value reflected at seat. So there's something to be said there. And be more than happy to discuss that in great detail or do some examples or running with you. The torque at which we start to measure angle. Okay.
I think we skipped one there from E.
We did. No, it was Mr. Trudeau's follow up and clarifying.
Oh, I'm sorry. Yep.
I got you in just a second, E. So the torque at which you start to measure angle. No, I think you're absolutely right. The snug point is the most reliable and accurate point at which to start measuring angle. And all things being equal, if you start to measure torque at your seat point or your set snug point, then ideally the angle measurement from snug to target would be within a standard deviation every time. However, that's not the case. You can get pretty close. I've seen applications get pretty close. But yes, I would start to measure snug point, start to measure angle at snug. In terms of the final rundown, however, I would encourage you not to discount the angle measurement in the rundown phase, as you can detect many problems in the rundown phase with angle that you might otherwise not have detected.
And as engineers, we hate this answer, but the truth is it's up to you. And so when Ben says that, his answer is right, because he thinks like I think, which probably most people on this call tend to think. We want some level of repeatability and consistency, not just on one program or one job, but from station to station to station. And so that's why Ben's answer is so good. What you want to do is you could set it at any point, really, as you enter that elastic zone. The catch to that is if it's different on, and not, I don't mean different in that the value is different, in that mindset isn't consistent. You know, why I set it at X on this station and, you know, Y at that station. If it's not something like snug torque, right, then the next person who walks up behind you might not have a frame of reference for that angle, because it's just a number otherwise, right? Whereas if you guys as a plant decide, hey, our rule of thumb for setting the angle start torque, where we begin to measure that angle, is by default our snug torque, then the person who walks up behind you has some frame of reference, right? They know that, you know, Ken was programming before me. We programmed the same relative way. We like to keep angle start torque, the snug torque, and then that 120 degrees or 10 degrees or 50 degrees or whatever that number it is, then it has a reference to them, right? Because you can help use that to figure out whether you've got a hard joint or a soft joint or something in between. And that's another great reason why that snug torque can help you do that.
Okay. So Emmanuel wants to know how burnishing the threads affects the final torque. This is fun. Well, very greatly, because what you're doing when you're burnishing the threads is you're adjusting the coefficient of friction between the threads and the application. I've heard two numbers that between 30 and 40% of all energy applied to a joint is lost to thread friction. Another 40% to underhead friction, and only 10% of the actual energy applied to any joint is actually converted to torque and clamp load. So if you're burnishing the threads, I mean, essentially what you're doing is you're polishing them, which there may be utility in. However, you've altered the coefficient of friction, and in so doing have greatly probably increased the amount of clamp load to torque that you're applying. It would be pretty much the same thing if you lubricated the threads with oil before you put them in. So as long as you know that that's what you're doing and why you're doing it, and it's designed for that, then that's fine, I guess.
Yeah.
You just got to make sure it's accounted for from design through engineering into manufacturing.
That's the big thing. You know, Ben's answer is spot on. I mean, that last point though is it's not necessarily right, wrong, or indifferent, I guess is the saying, but what matters is that it's consistent, right? What matters is that normally what we see is like oiled bolts, you know, or oil, like a mist or residue will even get on a box of bolts, and all of a sudden they're snapping bolts and they're saying, well, I don't understand it. You know, the torque is the same and the bolts are snapping. Well, that's because that coefficient of friction is so much lower on the bolt that has oil on it that you're applying an exponential amount of clamp load. And it's a drastically different fastener. So as long as the joint is designed around that, whether it be a burnishing or an oiling, then just make sure it's always there. Because if you had the opposite problem, you would run into something similar where your torque goes to a certain value, but you have much less clamp load than you're expecting. So the consistency there is really the important thing. Was it designed to have that or not have that? And is that what you're getting in box of bolts or bolts or screws, you know, one after the other?
Yeah, we get those calls. I don't want to say all the time, but we definitely get those calls where, you know, an engineer will call us and say, hey, you know, this tool stopped working, and, you know, come to find out after we do the analysis, it's because, you know, some well-intentioned person in purchasing bought a different batch of bolts this time. You know, same pitch, same length, same whatever, but there's a slightly different finish on it. And that's changed the coefficient of friction and started to fail joints.
So the next question is about picking the correct washer, lock washer, serrated nut, etc. for the job. Truth be told, honestly, I don't really have a great answer for that one. I don't totally know. That is typically done by the design element of the part, you know, of the fastener itself. It tends to be a different series of physics, right? So they're trying to provide that clamp load across the surface, you know, based on the washer size, right? So you're going to spread the load over a larger area. The lock washer, the serrated nut, you know, nylock, why do they put Loctite on it? Those tend to be around creating a friction, a residual friction, so that the bolt itself or the nut doesn't back itself off. So on the tool side, I don't have a great answer for that. But no.
I don't either, honestly. You know, I guess I'd be happy to have that conversation offline, maybe learn a little bit more about the specific concern or request, or get to understand what we're really getting at here. Just dig a little deeper on it. So if you want to, I guess, if you want to get my email, or I don't know, Stephen, how we do that, but
Just put it in the chat.
Okay. Yeah, I'd be more than happy to have that conversation. And I guess, you know, Kyle, in building this, I totally neglected to distinguish, really, aside from your one slide, the difference between static and dynamic torque, um, in terms of measuring it and understanding it, uh, and why it's different. You did a good job talking about it, you know, but they're completely different measurements. Um,
We talk a little bit about that because I think one of the most common things we get is the tool said 50, but so and so measured it over there and they got 42. Talk
yeah,
about that a little bit.
yeah. So I guess that's when. Let me see if I can get to that slide real quick. It was one of your slides. You did a good job
Mhm.
talking about it. There it was. We'll just talk about it a little bit more, right? So if the tool said 50, right, that was my peak dynamic torque. And over there, later on, they measured it at 42. Um, you know, that is the difference, the exact difference between dynamic and static torque. And so what we have to make sure of is that neither one is right or wrong, really. We just have to make sure that everybody's consistent. Um,
Yep.
and so if our plant standard is dynamic, then we have to measure dynamic, and the static measurement must be in line or accounted for with dynamic. If the plant standard is static, um, then that just has to be the standard, and we'll adjust the dynamic fastening so that we get
Yep.
good static results later on. Um, you know, um, but they're totally different. Um, and so when we do get those calls from time to time, and that's the conversation there, is that neither one is necessarily right or wrong. Um, it just has to be consistent.
Yep. That's the big thing. And when you're talking to the different people in the plant who are stakeholders in torque and quality, you just need to make sure that everyone's talking about the same one,
Yeah,
right? Because it's very commonplace to just say the torque. The torque is no good. Well, what torque? When was the torque taken? Was it from the tool? Is it from your wrench afterwards? Is it, some third device altogether, right? Because most of us typically will take a reading from the tool. There might be a quality group that comes around and sort of audits it later. Um, or they might take in station readings, and if the quality group is taking the same measurement 6 hours later as it's vibrated down the assembly line, their reading, their residual torque is probably going to be lower than the person who tightens it and then immediately comes behind and takes a reading. But even if I tighten it and then I immediately come behind and hit it with a smart wrench, those values are probably not going to be the same. I'm not going to say never, because every time you say never, it happens, right? But it is extremely unlikely that they will be the same. They should be consistent. The dynamic torque should be consistent with other dynamic torques. The static torque should be consistent with static torques, but they are not likely to be the same.
yeah, um, yeah. There's lots of reasons. You know, that relaxation happens for lots of different reasons. Um, I think one of the wildest examples that I ran into was a tier customer was facing a complaint from an end customer, the OEM, and they made, plastic. They fastened plastic parts into larger assemblies that went to the final OEM, and um, because they were using, current controlled tools, we were able to go back and look at their data history, right? And we could see that the history for the last 10,000 rundowns was consistent. They had solid data. They were hitting the design torque. However, I guess when these parts went to the OEM, they were no longer in spec. So one, we found out eventually that it's because it was July and they were plastic parts and very susceptible at low torques to, atmospheric effects. But two, good news story, they were using, data collecting tools. So we were able to go back through their data and sit down with them and the OEM and discuss that they were hitting the design spec. It was not the customer's fault. So that was pretty interesting story.
Looks like we got a question here. What is the best way to determine if there is a tool failure or if your transducer analyzer is failing while trying to measure the dynamic torque? So that's a great question. The good news is today, and this is pretty unusual with most things anymore. In the old days, when you had like a pulse tool that you set to a torque, even a shut-off pulse tool, the tool might shut off, but you didn't really know, right? And I think that was one of the common quality failure modes our customers had. With an electric tool that has a transducer in it, that transducer is measured and analyzed throughout the rundown process. Normally what would happen in that failure mode is the tool just doesn't work, right?
Yeah.
It just won't run, because most tools today are running sort of a system check prior to tightening. And so the tool will usually just shut off. It'll shut down. It won't run, and it's like it'll have power. It might blink, it'll do whatever the error mode is, but it is not normal that it'll allow you to tighten. If it were to happen, so we do have some customers who can't even risk the failure during like a single fastening, right? So they don't even want to risk it. Typically, we're talking about like a steering column or something along that nature. That is, the failure is so critical that there's almost certain injury and or death, right? So what we would typically do in that case is we would add a secondary transducer.
Transducer.
You'll hear it called, like Ben said, a redundant transducer. So what happens in that rundown is the two transducers are actually speaking to each other. One is the primary, so one is the one that's measuring, and the second one is measuring, but it's really comparing its measurement to the first one. It's not saying shut off the motor. The first one says that. The second one is really comparing what it does, almost like a calibration, to the first one, saying, are you within some level of expectancy from me, say 1 or 2%? And as long as that gap stays narrow, you'll get both readings, but the system is assuming that everything is functioning correctly. Where if you would have some sort of separation between those two values, they would say you need to check these transducers. One of them is having an issue.
Yeah. And I guess the only other real way, if you suspected something like that, aside from that, your tool will likely not run in that case, is to have an external transducer that measures dynamic torque, like an inline rotary transducer with some off-board analyzer. There's lots of those that we could recommend. So
that kind of leads you to the next question about that.
Yeah, well, I got 3 of them that rolled in all at once. Okay. So are there hand tools with 2 transducers? Not that I know of. Kyle, do you know of a hand tool with 2 transducers?
Not really. What you would do in that case, it typically, those functions like we were talking about are in such safety critical applications that you would have a fixtured tool because you want to control everything about it. In a hand tool, you do introduce some variability just because you have an operator. You have some inconsistency in terms of like angle of approach, how tightly they hold the tool if it reacts. Those will impact your final torque value a little bit. Typically, it's negligible, but in cases where you have 2 transducers, you're not going to take that risk. Ben's point before, what we would do to calibrate a tool, right, is we literally do exactly what we were talking about. So when you calibrate a DC electric transducer, you put a secondary rotary digital transducer on the front of that tool between the head of the tool and the fastening. And we're doing just like we were describing. We are comparing the result of the master transducer to the result of the control, the tool. And we are saying those must be within some allowable limit. And so with a DC tool, a direct drive DC tool, we would say that it has to be within 2%. That is a process that that some of our customers even do. I mean, it's not exclusive to us. We didn't make it up. But a lot of times inside like tool rooms or tool shops in a factory, we would always recommend, and this kind of goes back to the first question above too, how do I know when my transducer's bad? Having a set of these, right? So that if a question comes up where something numbers don't add up, or people are saying, look, it's saying it's tight, but it's not tight, right? Getting that out there, putting that secondary transducer that is known good on the tool and saying these should match within some reasonable amount. And you want to talk a little bit about those real quick, Ben?
Yeah, we have two more sitting there, but Mr. Durbin is the one that was asking the question that we talked about when trying to measure the dynamic torque. He clarified a little. And he was talking about an inline analyzer rotary.
So we're approaching his question, at least.
So, yeah, kind of, I guess. So I guess kind of what you were saying, Kyle. I mean, the foundational assumption has to be that the inline rotary is good.
We get that question from ISO all the time, though, and the way you have to think about the known, your master needs to be calibrated at an interval, right? So obviously you want to make sure you're well within calibration, that's calibrated by someone who is ISO 17025 like us, who knows what they're doing. But the second part of that is you are typically measuring other transducers, and so the numbers should line up. They normally do line up. And so even with your known, what we consider the master of the known good, if I put the tool to 50 and I know this tool was working at some level, right? And the tool says 50 and the transducer says 40. And I've adjusted the tool, I've done these things and they just never really line up, then the next thing you would do would be to check the master on a known good tool, right? So the nice thing is with a DC electric tool, you always have two gauges, one to bounce off each other. So you're assuming the master is known good, but if it continues to give you different results or strange results, you have these other devices, the secondaries, that at some point, if that tells you every secondary is bad, right, that outcome is unlikely as well. So in a sense, like in our laboratory, we say that we are testing our masters on almost every tool and typically they won't be off a little bit. Typically, if there's a problem with one of these digital transducers, they either first don't work, which is sort of the best case because you just can't use it, something's wrong with it, or two, they're off by a significant amount to where there's a pretty obvious problem, right? In the old days of an analog transducer, and I'm going down the well here quick, but in the old days they were analog, right? So most of us know what analog is, right? There was the length of the cable of the tool actually mattered, and they would have to actually set that, and we would put resistors in the back. I don't know if Ben's ever seen these. We would actually put resistors in the back of the analyzers depending on which transducer was in there. That's how you sort of set it up for the transducer. But now everything is digital, and so all of that is done inside of the tool or inside of the secondary transducer itself and transmitted as a data packet. So when there's a failure in that, it sort of shuts off. Yeah.
All right, let's hit one of these. We got two more sitting here right now. This is fun. This is way funner than talking about slots.
Yeah.
So issues breaking bolts, moving from pulse tools to DC in some applications. Could this be because of friction, creating heat in the bolt due to direct drive versus pulse, or something else? I'd say most likely something else. If they're pulse tools, like in my head, I'm envisioning pneumatic pulse tools going to a direct drive DC tool. So if that is true, right, and you can tell me if it's not, but if that's true, what we found before is that if you take one of these smart wrenches, like is up on the screen right here, and you went and measured that bolt that's fastened with a pulse tool, you'd find that it's not as tight as you think it is. And so that's kind of one of the growing pains, I guess, in a sense, of moving to a DC tool that is digital and computerized and electronic, is that it's not that we're suddenly having all of these bad parts or these issues or errors. It's just that they were there all along, but we didn't know it. And now the tools are showing us that these issues exist, either because the torque is of the tool, the DC tool is fastening higher than the pulse tool, right? Even though we thought that those torques targets were the same, they're actually not. The only time I've seen something like you're talking about occurring was in plastic, when we were actually just running too fast for plastic and we're melting the plastic in the rundown phase.
And we didn't talk about stripping, but essentially stripping a hole or a plastic piece is just like the bolt failure. You know, it's a different failure, but your curve will look a lot like what the bolt looks like. The curve rolls over, usually quicker and steeper. But Ben's right on. Typically what you'll find is either one, they weren't as tight as you thought they were with the pneumatic pulse tool. Or two, this could be a question, we touched on this a little bit earlier, like Ben was saying about speed. And with a DC tool, if it's a hard joint, you could be going too fast into the joint. And I know that sounds, you know, like how hard could the joint be? How much torque could I apply so quickly? I would have told you that, you know, it's minimum 10, 15, 20 degrees. I can tell you about a customer I had with a bolt into a frame that went from about 5 Newton meters to 65 Newton meters in less than 5 degrees of rotation. So if you're going too fast, even for a few degrees on a super hard joint,
Yep.
you'll break bolts.
Yeah.
So what you might want to do is lower that downshift point and go slower into the end.
Yeah, that might help. Yeah, you might be surprised how much, you know, when you hit that point, that seat point or snug point, how much kinetic energy and inertia and momentum you're carrying into that exact point of the curve. I mean, some of these DC tools run upwards of 3,000 RPMs. So, I mean, it's entirely possible. It's something to explore. I think it's most likely the first thing, though.
Yep. So he was saying right now he does have pneumatic pulse. So the first thing would be to check if you could fasten one with a pneumatic pulse, pull it with a wrench, see what you're actually getting. You know, because the way that pneumatic fluid works. Yeah, or the way the hydraulic fluid works in a pneumatic pulse tool is think of it like oil in your car, right? Is in the beginning, it's very viscous, it's smooth, it's easy to move. And then over time, it wears, it thickens, it has contamination in it. And it is harder for those mechanisms to move inside of there. And you're not, part of the force essentially is lost, is not transferred through to the socket and to the bolt. One of the benefits of DC tools and DC electric pulse tools is you don't have to do that.
All right. I promise we're going to get to this other question there, Mr. Howard. So, yeah, Mr. Britton, why don't you just reach out to me? I'd be interested to see this myself, or the sales engineer, your applications engineer, wherever you are. We can definitely work through this with you. We've run into things like this before, so we can certainly help you through this.
If you email Ben or I, or chat in, you know, your email address and like your city, state, we can pair you up with our person in that area. I mean, the one thing about torque, and, you know, even me as an engineer, I hate to say it, is it's not that there's not physics, right? And everything doesn't obey the law of physics. There's just so many different possible contributing factors that's why I never say never, right? I mean,
yeah. It depends.
Yeah.
So the other question we've got sitting here is can clamp load be affected after dynamic torque going into relaxation? I mean, short answer is yeah, absolutely. That's exactly what we're referring to. Now I'm regretting it, but in building this deck, I actually bypassed the slide that showed that exact thing. As you move in time away from the dynamic fastening, what happens in that joint, there's several things that occur. We call it settlement or embedment. There's all kinds of other things that occur. Depending on the materials, I mean, you could run into atmospheric or environmental impacts. But yes, all of those things, all of those factors at the end of the day will affect your clamp load. And that's why, you know, it's kind of important to make sure that the audit team or how you're measuring torque is consistent. Because as you get closer to ship time or delivery time, we need to make sure that depending on the materials in the joint, that we haven't dropped so low in the residual torque that we've now fallen under some acceptable level of load, because then post delivery we could have significant issues. So yes, as you move in time away from dynamic torque, that's exactly what happens is the clamp load begins to reduce to some degree, variable depending on materials. But yes, that's exactly what happens.
So when would be the best time to check this? I think you're going to have to try a little bit of trial and error on that. So there's, again, no perfect answer. It depends on a lot of things. It depends on how much vibration you expect your part or your final, your final product to endure. Really what we're talking about is, and I think Ben explained it well, is that, as you fasten, the parts at a microscopic level grab together and friction holds them together. But then over time, as they vibrate, they actually loosen and straighten. And when that happens, we've clamped them with an object, but now I've straightened and made them flatter, essentially, for lack of a better word, in that fastener. And so it is not necessarily filling that gap as much, or the gap is too large, essentially, for the two pieces as they've flattened out. What I would do, and you should see some leveling off of the settling torque, like it doesn't go on forever, essentially. I would check it, at the next station. I would check further down the line. I would check some sitting on the dock. Typically what our customers will do is they will do it in intervals so that they don't get out the door, right? So if this is my first process, I can do it much later in the process, because I have time between the first process and the end. If it is something where it is at the end of the line, I need to do it almost immediately, and then again before it goes out the door. So there are ways to condition a joint, and I know we didn't touch on that too much, but one of the things you can do, and some tools sort of lend themselves to this, you almost create that vibration or that settling as you're fastening. So particularly DC electric pulse tools do a very good job of this typically, because of the vibration why they're fastening. They are actually sort of forcing this event to happen immediately, as opposed to letting it happen naturally over time. So if this is a concern where you're seeing this and you're having trouble tracking it down, we've solved that problem with some customers by using that technology.
Yeah. I mean, periodically, from the time of dynamic through the end. I mean, I think you're exactly right, Kyle. You'll see it level off over time. There may be an initial steep drop off. That's usually what happens. Several Newton meters or several foot pounds initially, and then over the course of time, it'll sort of flatline across, kind of like this graph shows, actually. I think, did we catch up on all the questions? I think we did.
I think we're caught up.
I think we are caught up. So before everyone dips out, I think we promised somebody a cooler.
Ben and I aren't eligible, so
Wah, wah.
you're supposed to. Yeah.
So it looks like Mr. Alec Miller from one of the Honda facilities is gonna be the recipient of the cooler. So Alec, if you want, please feel free to send myself or we'll get in touch. We have your email address and we'll get your shipping information. So,
all right. Well, congratulations, Alec. We are hoping to do more events like this particular one again, just because we know engineers are always changing roles and coming out of school and needing this type of basic information. But we also want to add maybe other series on data analysis or programming classes, on certain brands, techniques. We hope again to get back to in person, if the world lets us someday, which I'm sure it will. But also this hybrid idea. So if there are certain topics you would like to see us cover, please let us know, either Ben or myself or Stephen, our marketing manager. So we really appreciate everyone's time today.
Absolutely. Thank you all.